We have talked about situations where an object has linear momentum, collides with another object, and then linear momentum is conserved. We have talked about situations where an object is moving in a line, but eventually will be part of an angular system or a rotating system. And so we consider that object to have angular momentum about a certain point. Here we consider an object that has both linear and angular momentum. Imagine perhaps a baseball bat thrown into the air, and the baseball bat spins around its center of mass. The center of mass point moves as if there was no rotational motion. Its linear momentum follows the path that gravity controls. But its angular momentum continues about that center of mass point. So this situation here is not quite as complex. This is a thin rod on a frictionless surface, perhaps on ice, and there is a lump of clay shot horizontally toward it, and it sticks inelastically to the end of the rod. And we're going to answer a number of questions about this related to both its linear and its angular motion. Let's start with question A here. We are going to determine the location of the system's center of mass immediately after the collision. Now the center of mass of the rod will be assumed to be at its center point, and the clay will eventually be stuck sort of here. And so it's logical to think about the center of mass as being in between the two of them, but we do need to show that is true. So let me grab a piece of paper here. Let's consider this point here to be our 0 point. The problem does ask us to determine the center of mass with respect to the left end of the rod. And so we could use torque. It'll be much more complex than if we just use the center of mass formula. The center of mass position will equal the sum of m times x for each piece of mass divided by the total mass. And so in this case, again, the mass of the stick is spread out evenly throughout, but we will consider it to be at the center point, or L over 2 from the end. And then the lump of clay also has a mass of m, and it is at the end point. We'll divide then by the total mass of 2m. You can see that our masses cancel. We end up with 3 over 2L divided by 2, or 3/4 L. Certainly goes along with what we were anticipating looking at the picture. The second question asks us to determine the velocity of the center of mass of the system immediately after the collision. And we want to find the magnitude and also describe the direction. The center of mass point moves as if there was no rotation, and so we can go ahead and just use the conservation of linear momentum to answer this question. So taking a look at our diagram here, the initial momentum will have to equal the final momentum being m times v. The stick is not moving at all, so that mass has 0 velocity and therefore 0 momentum to begin. And the lump of clay is moving at an initial speed of v sub o, upwards. After it sticks to the rod, we will have a mass of 2m moving at some unknown velocity, which we'll call v. That's 0. These masses cancel, and so we find that the velocity of the center of mass, the translational velocity of the whole system, is v sub o over 2 and it will continue to point in that same direction, upward. All right, now let's take a look at the angular speed of the system just after the collision. Now, some people might be tempted to do something like, say, v is equal to r times omega. The issue is that we know the v for the center of mass, so all we could use that to determine would be the omega of the center of mass, but that doesn't make any sense. The center of mass is not rotating. So this formula is not going to help us just quickly convert between omega and v. What we'll need to do here is to use the conservation of angular momentum. So let's come back to our page here. The angular momentum that we begin with will have to equal the angular momentum that we end with angular momentum being I times omega. For our system here, we begin with just an object, the lump of clay, moving in a straight line. So we'll have to consider the fact that it moves about point, the new center mass point, which I'll mark here, the new center mass point. And so this is the distance here that we will use for r. Again, that distance is chosen between our particle and between the expected point of rotation. So I times omega, that's the initial, will be just m times, the initial momentum, I times omega, will equal m times r squared times omega. In this case, we can make the connection between v and omega because the lump of clay is not at the center of mass. It is a distance away, so we do have a value of r to work with. We'll make the substitution then that r is equal, that omega is equal to v over r, and then we can cancel a value of r. And then again, coming back to our picture here, r is the distance between the lump of clay's position and the expected rotation point, the center of mass, for the new system. And so that is going to be, remember this was 3/4 L, so then this distance would be 1/4 L. So let's call that L over 4 times, and our speed is v sub o. So this is our initial angular momentum, m times L times v sub o over 4. To find our final angular momentum, we're going to need to know what I for the system is. So that's going to include I for the thin rod and I for the clay, which of course we were just working with. The rod, though, we would start with ml squared over 12 for the thin rod, but there's an adjustment that needs to be made because it's no longer pivoting around its center of mass. It's pivoting around the center of mass of the system. Okay, and so looking back at our picture here, here is the center of mass of the rod, here's the center of mass of the whole system, and so this will be our shift H. And you can see again that that is L over 4, 1/4 the length of the stick. So coming back down to our work, so that would be the rod, and then we also have the clay. Alright, so let's start to put some pieces together here. m times L squared over 12 plus m times, and h is L over 4, so when we square that, that'd be L squared over 16. And then for our piece of clay, also with a mass of m, and the R value again is L over 4, again L squared over 16 when it's squared. Alright, so now it becomes a little bit of algebra. There's a number of different ways that you can handle this. I would pull out the ML squareds, and I would look for a common denominator here. So this would be 4 over 48, 3 over 48, and 3 over 48. So that comes out to be a total of 10. And so then we can reduce that a little bit. The I for our system is going to be 5 ml squared over 24. Alright, so finally we can use the initial angular momentum and the I here to finish off this question. The omega that we're looking for will be the initial angular momentum divided by the system value of I. Cut that off again. Omega equals initial angular momentum divided by I of the system, and that would be let's see, ml v sub o over 4 divided by 5 ml squared over 24. Do a little algebra here. Cancel our m's, cancel one of our l's, and notice that we have a 4 and a 24. We can reduce that to a 6. So I'm going to swing the 6 up here and then leave the 5L below. That is our value for omega. Alright, let's continue on with this question. The goal down below here, determine the change in kinetic energy as a result of the collision. Okay, and so what we're going to need to be thinking about here is finding the change in kinetic energy as being the final minus the initial. So we want to find both of those values, the final value and the initial value. Keeping in mind that when things move through space, our kinetic energy is mv squared over 2, and when things are rotating, the kinetic energy is I omega squared over 2. So initially we just have the clay moving in a straight line, so we just have the one type of kinetic energy, and then afterwards we have everything moving through space, translating, and then also spinning about the center of mass point. So we'll have both. Let's start with the initial kinetic energy. That's just going to be the mass of the clay times the initial velocity squared over 2. Alright, unfortunately that's the easy part. The final kinetic energy is going to include the total mass of the system, the overall linear speed of the system, remember that was v sub o over 2, square that, and then divide by 2. So that's the mass times the v squared divided by 2. And then we'll also have the rotational kinetic energy, and so we'll need to use our value of I from the previous part. That was 5 ml squared over 24. And we'll need to use the omega value from the previous part, 6 v sub o over 5L. And then, of course, divide by 2. Now, if you can get to this point, you'd want to say this minus our mv sub o squared over 2 and sort of be done with it. Taking the AP exam, maybe sort of give up that last point. But let's work through the algebra and prove that we can do it. This section here I could eliminate a factor of 2, and so then we're left with just m v sub o squared divided by 4 when I square that term. And then over here, let's see what we could do. I think I better multiply some things out. So this is going to be 5ml squared. Let me do this here, 48, 24 times 2. And then let's square out this fraction, 36 v sub o squared over 25l squared. Let's see what we can simplify. So got an L squared and an L squared, that's good. I'm down to the variables I'm expecting. 48 and 36, they have a 12 in common, so let's reduce that. 5 and 25 have a 5 in common. And so this can be rewritten as 3 mv sub o squared over 20. Alright, so this represents the, this, again here, 3 mvo squared over 20 plus the translational kinetic energy. So that's the kinetic energy at the end. And then we would need to subtract the initial kinetic energy. This would now represent the change. So this is the final, that's the initial. Alright, let's see if we can find a common denominator. Looks like 20 would work. So we have mv sub o squared all times. So we have 5 over 20, and this would just be 3. And then this would be 10 over 20. So we have negative 2mv sub o squared over 20, or negative mvo squared divided by 10. So that's our change in kinetic energy using the variables given in the problem.